Good morning po, classmates and Sir Nats.
Good morning.
My report for today is about the quality control in the radiopharmaceuticals. What is a quality control? Quality control is a procedure or a set of procedures intended to ensure a certain level of quality in a product or service. The QC process involves identifying standards for quality, regularly reviewing products to ensure they meet those benchmarks, and removing any products that do not meet quality expectations. QC also certifies that the values for individual tests are compliant with what is prescribed in the relevant documents. What is a radiopharmaceutical? Radiopharmaceutical is a radioactive compound which possesses diagnostic and/or therapeutic features for human diseases. The World Health Organization describes the radiopharmaceuticals as unique medicinal formulations containing radioisotopes which are used in major clinical areas for diagnosis and/or therapy. Most of the uses of radiopharmaceuticals in nuclear medicine are administered for diagnostic purposes. Usually po, they are administered in the patients intravenously, and it is obviously used for human use. So they must undergo a strict quality control measures. The radiopharmaceuticals are a combination of radionuclide and the pharmaceuticals. These are also used to produce images of organs or tissues of interest. The quality control procedures are always performed prior to patient administration, and the main purpose of the quality control is to ensure that the radiopharmaceuticals are effective, toxicologically safe, and contain known ingredients of known quality in known proportions and predetermined purity. So the presence of impurity may cause unnecessary radiation and burden to the patient. Quality control in radiopharmaceuticals is crucial and involves two different aspects that includes pharmaceutical parameters and radioactive parameters. In pharmaceutical parameters, it is designed to ensure that no microbiological, pyrogenic, or particulate contamination can harm the patient. And for the radioactive parameters, it is designed to ensure that enough or the intended radiation exposure of patients is kept to a minimum.
Jem, may I just add something before you continue? Okay. As what Jem is telling us, quality control is at a certain level, and normally, of course, when people talk about quality, it is the highest level of confidence. Okay, so highest level, and of course, the minimum level would be compliance, as what Jem is telling us, compliance to certain standards. Okay, now in terms of pharmaceuticals, there are several standards that are out there. Of course, here in the Philippines, when we talk of radiopharmaceuticals, the PNRI, for the Philippine Nuclear Research Institute, which is the competent authority in the country, follows suggestions of the US Pharmacopeia. But of course, you would also know that some other standards like the European Pharmacopoeia are also out there. So it depends on uh, whether the facility, say a nuclear medicine department for our purpose, would add some other suggestions that may be different from the ones suggested by the Philippine Nuclear Research Institute or the US Pharmacopoeia. So sometimes they also do that. Now, another point I would like to raise is that uh, in the nuclear medicine department, since 80 to 85% of the personnel are medical technologists who went into nuclear medicine technology, are the ones performing the QC test or the quality control test. However, it is suggested that on the checking of the results of the QC performed, it should be another person, not necessarily the same person who did the production and the uh, process of acquiring the radiopharmaceutical. So it is suggested that another person be the one to check on the quality control. So if that nuclear medicine department has a radiopharmacy or a radiochemist, the nuclear medicine technologist is the one performing the analysis and checking of what the other person had done. Okay, so it depends on the nuclear medicine facility. Now, in the case of the Philippines, there are not much radiochemists or radiopharmacists, and that's the reason why a nuclear medicine technologist who is a licensed medtech is also the one performing it. But as I've mentioned, it should be a different person who would check on the things done by the nuclear medicine technologies. Okay, so now we're going to hear a lot of the details that Jem has mentioned here. Okay, please continue, Jem.
Thank you, sir. The quality control also involves several specific tests that includes purity, potency, biological safety, sterility, and efficacy. So what are the tests that we analyzed in the QC of radiopharmaceuticals? We have the physical, chemical, and biological. For the physical test, it it involves a visual inspection to recognize the size and state of radiopharmaceutical. A true solution should not contain any particulate matter, and any deviation from original color and clarity should be viewed with concern as this can alter its biologic behavior. The solution ideally should be clear, colorless, and free from any particulate matter, but some radiopharmaceutical solutions have a slight yellow color due to its preparation, and it is still considered acceptable.
Uh, Jem,
Yes,
uh, would you have a reference for that recent statement that you mentioned regarding a slight yellow color? Were you able to get some specifics on that? The reason why I'm asking is because before, when I was with the pet center of St. Luke's in Quezon City, we had occasions of yellowish solution for N13 ammonia. This N13 ammonia is a positron emitter and produced from bombarding or oxygen 16 from ordinary water to become nitrogen 13. So as what you have mentioned, it, the ideal physical characteristic of a radiopharmaceutical should be clear and colorless. However, you mentioned that there are certain occasions when slightly it is yellowish in color. Later on, if you go back to that reference that you mentioned. Can you share it with me?
Yes, sir. I will have to find it po with my list of
Yeah, because
references.
uh, the radiochemists that we had before, of course, we did not use them. No? We did not use them. And when we had that occasion of asking the other guys during that time, especially those pet centers abroad, they would not have any definite suggestion on what's the reason or what would be the solution. So maybe yeah, you can share that with me and with us later on. Okay,
Okay, so perfect po.
thank you, Jen.
For the chemical tests, we have the pH and ionic strength. All radiopharmaceuticals should have an appropriate hydrogen ion concentration for their stability and integrity. This aim is to determine the pH of a solution by a colorimetric evaluation with pH paper. Ideal pH of a radiopharmaceutical should be 7.4, and pH can vary between 2 to 9 because of the high buffer capacity of the blood. For the radionuclidic purity, it is a fraction of the total radioactivity in the form of the desired radionuclide present in a radiopharmaceutical. A compound has absolute radionuclidic purity if it contains no radionuclide other than one of interest. Impurities arise from extraneous nuclear reactions due to isotopic impurities in the target material and fission of heavy elements in the reactor. These impurities can originate from the undesired nuclear reactions because of the isotopic impurities in the target material. The undesirable radionuclides may belong to the same element as the desired radionuclide or to a different element. Impurities may be removed by appropriate chemical methods, and the radionuclidic purity is determined by measuring the half-lives and characteristic radiations emitted by individual radionuclides. One of the methods to determine the radionuclidic purity is the high-resolution gamma-ray spectrometry. It is the only fast, precise, and complete analytic method available for radionuclidic purity determination. It has a precise measurement of the gamma ray proton energies that is emitted by different nuclei, and it can establish nuclear energy level structures that allows for the identification of the trace radioactive elements through their gamma ray emissions. For the radiochemical purity,
Jen,
yes, sir.
can I add something about the radionuclidic purity?
Yes, sir.
Okay. There is, if you go back to the previous slide before
This
that,
right, sir.
the other one.
This one po.
Yeah, thank you. A compound has absolute radionuclidic purity if it contains no radionuclide other than one of interest. Okay. I would like to cite an example for a radionuclidic purity test that is done for technetium-99m generated from a molybdenum-99 generator. If you would recall, when we talked about the production of radiopharmaceuticals, one of the ways of producing a short-lived radionuclide is with the help of a so-called generator. And the most common generator used in nuclear medicine would be the Moly-99, technetium-99m generator. Now, the PNRI also suggests that there is a limit on the amount of molybdenum-99 that should be present in the eluate. The limit is if the amount of molybdenum 99 is more than 0.15 microcuries per millicurie of technetium 99M solution, then that uh, eluate or that product derived from the generator should not, I repeat, if it is more than 0.15 microcurie of moly 99 per millicurie of technetium 99M, then it should not be administered to the patients. So that means you should do another elution. Okay, so that eluate should not be administered to patients. Now, how does one perform that? Of course, the performance is another alternative to the one suggested by GEM on using a high gamma ray spectrometry machine. But the simplest way to do that, no, would be after the elution of the technetium 99M. Of course, we measure how much activity is generated with the dose calibrator. So that would provide us the activity, and generally that is in millicurie units for the technetium 99M. So now you have your denominator. Now the next thing would be to put that eluate in the extraction vial inside a so-called molybdenum pig. A molybdenum pig is actually a 3 millimeter thick lead container that you place your technetium 99 and that was generated and then placed in your dose calibrator. And after setting for the moly 99 generation of the activity, you would now get your numerator for that ratio. So the amount would be in microcuries. Okay. Now, what is the significance of the 3 millimeter thickness of lead? Well, the 3 millimeter thickness of lead is referred to as a 10th value layer. Now, 10th value layers or TVLs are thicknesses of materials that would let the transmission of certain gamma energies to just 10%. So that means that is the 10th value layer for technetium 99 and 140 keV, meaning the energy from technetium 99M will not be able to penetrate the 3 millimeters. Therefore, if there is a significant amount of molybdenum 99 energies, that will be the only ones that will be emitted. So now you have your equation. So you would have your data for the denominator, which is the activity in millicuries of technetium 99M that you have generated. And for the numerator, you would have the activity of molybdenum 99 in microcuries. So if you divide that, if the quotient or the answer is more than 0.15, therefore we should not administer to patients. Okay, so that is another example. And as what Jem has been telling us, most of these radiopharmacy labs, meaning those that produce their own radiopharmaceutical, would have setups like what Jem has told us, a spectrometer, a high gamma spectrometry system to check on whether there are other significant amounts of radionuclides present in the produced pharmaceutical. Okay, thank you, Jen.
Thank you, sir. The next is the radiochemical purity. It is the fraction of the total radioactivity in the desired chemical form in the radiopharmaceutical. It is the radiochemical form which determines the biodistribution of the radiopharmaceutical form. Impurities arise from the action of the solvent, a change in temperature or pH, the light, presence of oxidizing or reducing agents, and radiolysis. The presence of radiochemical impurities may result in poor quality images due to high background from surrounding tissues and blood, and provides unnecessary radiation dose to the patient. The composition of labeled compounds by radiolysis depends on the specific activity of the radioactive material, the type and energy of the emitted radiation, and the half-life of the radionuclide. The stability of a compound is time-dependent on exposure to light, change in temperature, and radiolysis, and the longer the compound is exposed to these conditions, the more it will tend to break down. So, there are ways to lessen the degradation of the material. Substances with antioxidants such as sodium ascorbate, ascorbic acid, and sodium sulfite are often added to maintain the stability of these radiopharmaceuticals, and some radiopharmaceuticals are stored in a well-closed containers and in well-ventilated areas. Analytical methods used to detect and determine the radiochemical impurities in each radiopharmaceuticals include precipitation, paper thin layer and gel chromatography, high performance liquid chromatography, and ion exchange. For the chemical purity, it is the fraction of the material in the desired chemical form, whether all of it is in labeled form. Chemical impurities originate in different areas, including the breakdown of the material, either before or after labeling, the inadvertent addition during labeling, and the undue accompaniment in the preparation of the compound. An example of this would be the aluminum is a chemical impurity in the technetium-99m eluate, and it can cause problems including toxicity.
Well, of course, as we recall, the molybdenum-99 is in alumina column. Therefore, there are chances of getting aluminum as an impurity, as what Jem has been telling us. Okay, thank you.
The presence of chemical impurities before radiolabeling may result in undesirable labeled molecules that may or may not interfere with diagnostic tests. Undue chemical impurities may also cause a toxic effect. Purification of radiopharmaceuticals from chemical impurities is often carried out by methods of chemical separation, such as precipitation, solvent extraction, ion exchange, and distillation. For the radioassay, the amount of radioactivity of a radiopharmaceutical before dispensing, as well as that of each individual dosage before administration to patients, must be determined. These activity determinations are carried out by using a dose calibrator. A dose calibrator is an instrument constructed to measure the number of ions within a medium. It usually consists of gas-filled enclosure between two conducting electrodes. When gas between the electrodes is ionized by any means, such as gamma rays or other radioactive emission, the ions and dissociated electrons move to the electrodes of the opposite polarity, thus creating an ionization current which may be measured. Each ion essentially deposits or removes a small electric charge to or from an electrode, such that the accumulated charge is proportional to the number of like charged ions. These ionization chambers are widely used in nuclear medicine, and it is used to determine the exact activity of radioactive dose administered to the patients. The performance of dose calibrator must be checked by carrying out several quality control tests such as the constancy, accuracy, linearity, and geometry. For the constancy, this indicates the reproducibility of measurements by the dose calibrator, and it should be performed daily. For the accuracy, it is determined by measuring the activities of at least two long-lived reference sources and comparing the measured activity with stated activity. It should be performed after installation, every year, and after repairs. For the linearity, it is the ability to measure the activity accurately over a wide range of values and should be performed after installation, quarterly, and after repairs. For the geometry, it varies in sample volumes or geometric configurations of the container. Correction factors must also be established for this as it changes in volume or container configuration, and it should be performed only after installation and after repairs.
Uh, are you going to mention, Jem, about the radionuclide calibration sources that are often suggested for this?
That's not in my
Okay,
reports.
okay. So I'll say that now. So guys, since Jem has mentioned that you need to perform the suggested tests like constancy test, accuracy test, linearity, and geometry, there are radionuclides that we refer to as simulators for the radionuclides used in nuclear medicine. As you would recall, the radionuclides that we use are very short-lived. Example, technetium-99m with a half-life of only 6 hours, or iodine-131 with a half-life of around 8 days. So if you use, for instance, technetium-99m for this test, remember Jem mentioned like for constancy, you should do it daily. So how could you do a certain standard technetium-99m source if the half-life is only 6 hours? So as I am saying, there are so-called simulators. These are radionuclides, meaning they are also radioactive materials that would simulate the energy of the radionuclide that is used in nuclear medicine. Now, one example would be cobalt-57. That's cobalt-57 that has a half-life of around 285 days. Now, the reason why cobalt-57 is used is because its significant gamma energy is similar to technetium-99m. Remember, technetium-99m has an energy of 140 or 140 kilo electron volts. Cobalt-57 has around 160 or 160 kilo electron volts. So that is very much similar to your technetium-99m. So nuclear medicine departments have cobalt-57 sources to simulate technetium-99m energies. Now for iodine-131, the simulator that is used is barium-133. Okay? Because obviously barium has a longer half-life than iodine-131, but would have energies that would simulate or be similar to iodine-131. And the third radionuclide, though it is not having a similar energy with any other radionuclides used in nuclear medicine, the reason for its use, I'm referring to cesium-137. Okay, cesium-137 has a gamma energy of 0.662 mega electron volts or 662 kilo electron volts. And the important thing about cesium 137 is that it can be used for the accuracy, for the linearity, and of course also for constancy that Jem has mentioned to us. It has a long half life. It's around 30 years. That's 30 years, no? So which is ideal for the tests that were mentioned by Jem. So in the nuclear medicine lab, they would have such sources in different configurations and forms. They can be in the form of rod-shaped sources that can be used for calibrating and doing the tests for your gamma well counters, or can be used for your dose calibrators, as what Jem has been mentioning to us, or they can be in the form of discs, discs or buttons that can be used for checking on the other equipment like uptake probes, okay, that we have talked about earlier. Okay, so these tests and the results of such are also required by the PNRI for submission, especially during the inspection that they would have annually. Okay, so please continue, Jen. Thank you.
Thank you po. The next set of tests are the biological tests, and these are carried out essentially to examine for a radiopharmaceutical to be safe for human consumption. We have the sterility test. This is performed to prove that radiopharmaceuticals are highly free of viable microorganisms, including bacteria and fungi. This must be performed aseptically so that external contaminations will unable to interfere with test samples during the experiment. A sterile laminar flow hood and well-trained personnel are a requirement to perform this task. One
Yeah,
of the,
sorry.
yes,
Yeah. You mentioned about a laminar flow hood. Can you mention to us the difference between a laminar flow hood and a so-called fume hood?
the laminar flow hood, sir, has a unidirectional flow of HEPA filtered air over the work area, while the fume hood um, is like the most common local exhaust ventilation system that is used in laboratories such as in schools po.
Okay, so guys, what Jem is telling us is that the difference between the two hoods would be the direction of the air, right, Jem?
Yes, sir.
So fume hoods are exhaust systems, so the direction of the air is going
Going.
inside, going inside the hood, outside, of course, no. But for the laminar flow hood, the flow of air is going out of the hood, meaning it does not let air come inside. That's the reason why in the sterility test, as seen in the bullet of Gem, must be performed aseptically, right? So no air should be coming inside the laminar flow hood. The direction of the air coming from the hood is keeping out the air, so it's blowing out. It is some sort of an air curtain, right? So to make the system and the process aseptic. Okay? So again, for the fume hood, it sucks in air. Okay, it sucks in air, and of course the direction would be to some stock and some filter systems like the ones mentioned by Gem, like HEPA filters and so on. Sometimes they also use uh, activated charcoal systems. Okay, so please continue, Jem. Thank you.
For the sterility test, we have to incubate the radiopharmaceutical sample in two different ways for us to detect bacterial and fungal contaminations. For the bacterial contamination, we have to incubate it in thioglycolate medium at 30 to 35 degrees for 14 days. And for fungal contamination, we will have to use the soybean casein digest medium at 20 to 25 degrees for 14 days. If a bacterial growth is observed in the either test, the radiopharmaceutical is not sterile. So this is actually one of the drawbacks of the sterility testing because the use of culture media takes longer than the half-lives of many common short-lived radionuclides such as the technetium-99M. And to solve this drawback, we have to incubate the radiopharmaceutical with growth medium containing carbon-14 glucose for 3 hours to 24 hours. The organism will metabolize the glucose, which results to the releasing of the carbon dioxide 14 gas, and the collection of this gas indicates the presence of both aerobic and anaerobic organism. Radioassay is done with gas ionization chamber and can be detected by this method. There are two methods of sterilization. There is the autoclaving and the membrane filtration. For the pyrogenic,
Sorry, Jem.
yes
Can you go
sir.
back to that? Okay.
Yes.
Okay. So one note that we should recall, as what Jem is telling us, is that uh, sterility tests are important. However, use of, let's say, culture media takes longer than the half-lives. Okay. The example that Jem showed us here is technetium-99M. And if you would recall, technetium-99M has a half-life of only 6 hours. And sterility tests like the growth test, okay, takes around 3 to 24 hours. Sometimes there are also tests that would require 14 days. So for radiopharmaceuticals that are produced like technetium-99M or the positron emitters that would have much shorter half-lives, this may not be ideal for the everyday check, meaning if you would like to check on the sterility prior to injection of the patient, then this is not ideal. So these tests that are done, like the growth test, autoclaving, are performed especially during the establishment of the radiopharmacy lab, or can be done also, but just to support the other tests for sterility that would provide results relatively at a very short period of time, or meaning very immediate. And that is the reason why Jem has mentioned about the second test. Can you go to that slide, Jem?
This one sir.
Yeah, the membrane filtration test. Now, what are membrane filtration tests? These are membrane filters that would have mesh uh, characteristics or dimensions that are smaller than the smallest size of the microorganisms, so that they will not be able to penetrate it. I'm just looking for a picture, okay, to show that. Okay, let me check on that first. Okay. Can I have the presentation initially, Jen, so that
I
I
see.
can show that, so that we will not forget it. Okay, thank you. Can you see my slide now, guys? Can you
Yes,
see my
sir.
slide? Okay. So this is an example of what I'm trying to say. Okay. Uh, a mesh. Okay. These are dimensions of the mesh. So the dimensions should be smaller than the smallest microorganism. Okay. Uh, I think I have a better one. Oops. Sorry. I have this one. Can you see this system? You have a syringe and a membrane filter. So the membrane filter is placed after the extraction of the produced radiopharmaceutical and before the collection in a so-called vial. So the radiopharmaceutical passes through this filter. Now, after it has been produced, they take the membrane filter and attach it to a syringe and plunger system where you do not have anything inside, it's just air. So, the way to test is to check on whether the filter membrane has been compromised, meaning if the membrane filter has been destroyed or had mesh that is not in its original form or dimension. So what they do is to place this syringe and this filter system into a beaker with water and press the plunger to let air out. So if bubbles, in some references, it is called a bubble sterility test. If the bubbles would come out above here, no, above the membrane filter, that means air is having difficulty passing through the membrane filter. That means the filter is not destroyed. However, if the bubble would come out after or below the membrane filter, that means the filter has been compromised. And if that is so, sterility is not assured. Therefore, we should not administer the dose. So again, if the bubble is coming above the filter, that is good. Bubbles coming under the filter is not good. Okay, so when this has been seen, normally the radio pharmacy will not administer the doses. And of course, the sample that was taken or the specimen that is taken will undergo the 14-day biological growth test. And of course, that would support the decision of doing another production of the radiopharmaceutical. Okay, so this bubble test is performed specially for very short radioactive materials like positron emitters and also technetium-99m. Okay, I'll give the floor back to you, Jem.
Thank you, sir. So the next test is the pyrogenicity test. All radiopharmaceuticals are required to be pyrogen-free because pyrogens are either polysaccharides or proteins produced by metabolism of microorganisms. An example would be the bacterial endotoxins. Sterility of a solution does not guarantee its pyrogenicity, and sterilization process does not destroy the pyrogens in a pharmaceutical, so there is no specific method for making a sample pyrogenic. Therefore, precautions should be taken from the beginning. Pyrogens essentially originate from the metabolism of bacteria. Hence, the best way to prevent pyrogenic contamination is to use sterile glasswares, solutions, and equipment under aseptic conditions in any preparation procedures. There are two tests to determine the presence of the pyrogen. The first is the USP rabbit test. It includes 3 mature rabbits weighing not less than 1.5 kilograms. Temperatures are controlled by keeping them in a space with uniform temperature. The test sample is injected into the ear vein of each of the rabbits, and temperatures of the rabbits are measured from 1, 2, and 3 hours after injection of the test material. So, how to tell if the sample is pyrogenic or non-pyrogenic? It is non-pyrogenic if there is a less than 0.6 temperature rise in the temperature in individual rabbits, and the sum of all the temperature in all the subject does not exceed 1.4 degrees Celsius. For us to consider it as pyrogenic, there is a rise in the temperature in individual rabbits of more than 0.6 degrees Celsius, and the sum of the temperature in all subjects exceed 1.4 degrees Celsius. The second test to determine the...
Jen,
Yes po.
sorry, can I just mention something? Can I share?
Yes po. Yes, please.
Okay.
Can I stop? I will stop po.
Yeah. Can I share now?
Ayan po.
For a while. Okay. Let me just clarify some things. For instance, on how we write the temperature difference. Jem mentioned about a difference of 0.6. Is that correct, Jem?
Yes, sir. 0.6.
So 0.6 Celsius degrees. This should be the way on how we write it. 0.6 Celsius degrees is not the same as 0.6 degrees Celsius. Okay? Of course, Jem, I know it was not you. You just picked that up from the reference. But what I'm trying to say is that it should be written differently because these two configurations are very, very different. Why? 0.6 degrees Celsius is talking of a temperature, while 0.6 Celsius degrees would mean a difference in temperature. For instance, uh, 4 degrees Celsius going to 4.6 degrees Celsius. The difference is 0.6 degrees Celsius. Celsius degrees, right? Can you get me? Another example would be 24 degrees Celsius increasing to 24.6 degrees Celsius would mean also 0.6 Celsius degree difference. But 0.6 degrees Celsius is a temperature between, let's say, 0 degrees Celsius moving to 0.6 degrees Celsius. But if you move, let's say, from, let's say, 25, let's say the temperature of the rabbit is 25 degrees Celsius, and after injection to the ears, to the ear veins of the rabbit, the temperature of the rabbit increased to, let's say, 26 degrees Celsius, then the difference is how much? How much is the difference, guys? For instance, the temperature of the rabbit before injection is 25 degrees Celsius. After injection, let's say after 1 hour, as what Jem has been telling us, because you have to measure the temperature at 1 hour after, 2 hours after, and is that 3 hours or 6 hours, no, Jem? Uh, the difference in the temperature should not be more than 0.6. So if, for instance, the data acquired was 25 degrees Celsius for the temperature of the rabbit before injection, and then after 1 hour, it rose to 26 degrees Celsius. First, what is the difference? How much is the difference? It is 26 minus 25 is
One, sir.
1 what? 1
One
Celsius.
Celsius degrees.
Okay. Bong, it's 1 only. So it's just an absolute number. So 1 Celsius degree and not 1 degree Celsius, because 1 degree Celsius is very, very cold, right? It's near zero. That is what I'm trying to say. It's the way we write it. So 1 Celsius degree is not the same as 1 degree Celsius. Malamig masyado yung 1 degree Celsius, right?
Yes, sir.
So, just to point out, guys, on the way we write the configuration. So 1 Celsius degree is a difference in temperature. 1 degree Celsius is a temperature.
Temperature.
Okay. Thank you.
Thank you, sir, for that clarification. Hindi ko po alam yan.
Yeah. You see that also in probably the reference that you have, they are writing it also that way, right?
Yes, sir.
Okay. So thank you. Please continue. And hopefully you correct that in the slide, okay?
I will correct it, sir.
Thank you.
Okay, the next test po for the pyrogen testing is the LAL or the Limulus amoebocyte lysate test. This is rapid and easier method and uses the lysate of amoebocytes from the blood of horseshoe crab Limulus polyphemus. It is employed for the detection and quantitation of endotoxin type pyrogens. The principle of this test is based on the formation of an opaque gel by pyrogens upon incubating the sample with LAL at 37 degrees Celsius. Reaction takes place within 15 to 60 minutes. For the biodistribution tests, the clinical efficacy of every radiopharmaceutical before their administration to humans must be evaluated by testing in animals and gets approved by the FDA. So this type of study includes tissue distribution, plasma clearance, urinary excretion, and fecal excretion after administration of the radiopharmaceuticals. To perform a distribution study, the radiopharmaceutical is injected into the animals such as mice and rabbits and ascertain the relative quantity of the radioactive in various organs. For the safety considerations, safety should be a top priority in any laboratory, and quality control sample handling should be performed in a shielded fume hood. This should be laminar wood, pero I will change it din po. Special precautions such as wearing personal dosimetry devices, wearing proper personal protective equipment, and following procedures that ensure that radiation exposure is as low as reasonably achievable are critical. Staff training is a must to ensure control over the radiopharmaceutical manufacturing processes in compliance to approved standard operating procedures. For the other QC tests, final product container should be checked for proper labeling prior to release of the product. The outer label on the package should include the name of the product and the name of the radionuclide, product identification code, name of the manufacturer, identification number, or it can be called the batch number. For liquid preparations, it should include the total reactivity in the container, concentrations per ml at stated date and time, and the volume of the liquid in the container. For solid preparations, total reactivity in the container at a stated date and time.
Then, sorry, is that reactivity or radioactivity?
Reactivity, sir, but I guess it's supposed to be radioactivity.
No? Kasi parang chemical yung pag-reactivity, right?
Reactivity, yes sir, I will have to edit this.
Yeah, okay. And please take note, guys, that it is important that you put also, after writing the activity, the stated date and time. As you would recall, radionuclides would have different activities, especially when they decay. So important for us to label the time and date. Okay, thank you.
For capsules, the total radioactivity of each capsule at a stated date and time and number of capsules in the container. And of course, the international symbol for radioactivity.
Normally, you would mention not only for radioactivity, that symbol for radiation, I think.
Radiation.
It would be a general source, yes, for radiation, not only for radioactivity. Okay? Because these signs, if you would have noticed are also used in X-ray rooms where you have X-ray sources. So it is the international symbol for radiation. Okay,
Okay,
and here
that's
is the trifold sign. Now, guys, sometimes you would have a different but similar trifold sign. Okay, this sign, as you would see, you have two on the upper side, two of the blades, the black blades. Can you notice that? They are on the upper half of the circle, and you have one black blade or fan shape below. Now, if you see a sign that is having one on top and two below, that would mean the beneficial use of radiation, which is used by the International Commission for Radiation Protection. Okay, just so that you would know. So this is the international trifold sign for radiation. Please continue, Jen.
for the labeling. We have wait, how many levels? We have 3 levels. First is the radioactive white one,
Where do we place this, Jen? Where do we place this label?
outside po of the package.
Okay, so this is, remember Jem mentioned that the label is placed on the vial. Now, if the vial is in a stored container, it is again placed on a so-called transport package. The transport package would have labels like this one, like what Jem is telling us. So these labels are placed on transport packages. Okay, thank you, Jem.
Okay po. The radioactive white one contains almost no radiation, and the maximum allowable radioactivity is 0.5 millirems per hour on the package surface. So if you see this logo, it means that it contains almost no to 0.5 millirems of radioactivity. The second is the radioactive yellow 2. It contains low radiation levels, and the maximum allowable radioactivity is 50 millirems per hour on the package surface and 1 millirem per hour at 3 feet from the package. Sir Nats, sorry, this one, I don't get this po. So, paano po yung
Yes.
itong 50 millirems and then meron 1 millirem per hour at 3 feet?
Okay. So what Jem is telling us is that, can you go back to the white category 1 white? Okay, so the category 1 white is telling us that if you have a radiation detecting instrument, before you place the labels, you have to measure the radiation emitted at the surface of the box or the package. Okay? If on the surface of the package it is 0.5 millirem per hour or below, you should use a category 1 white. Now, if the radiation level is above 0.5 millirem per hour, but not equal to 50 millirem per hour at the surface, you use category 2 yellow. Next slide, please.
This one.
Yes, this one. And you should also measure the radiation levels 1 meter or 3 feet from the package. You get me, Jem?
Yes, sir.
So, ididikit mo yung radiation detector mo sa surface. So, measure it. If the radiation level measures 0 up to 0.5 millirem per hour, the package label should be white.
White po.
Okay, so kung 0.5 up to less than 50 millirems per hour, you use category 2. yellow.
Okay,
So
sir.
if you have more than 50 at the surface, that is category 3, yellow, right?
Yes, sir.
And the measurement at 1 meter or at 3 feet from the package should not be more than 10 millirens per hour.
Thank you po,
Okay,
sir.
so the benefit of the labels that we see would be at a distance, you would know how much radiation is emitted from that package. Now, of course, you would see in the label, you have content, meaning what is the radioactive material inside the container and what is the activity. Now, there's another box, transport index. Can you see that? Or can you zoom in, Jen?
I don't know how to zoom in, but
Okay. But can you,
wala. Ay, wala.
balik mo lang yan. Can you focus
Ano
the
po?
yeah, that is transport index. The transport index is a number also that is telling us how much radiation is emitted from 1 meter away. So if the measurement of the dose, let's say, is 10 millirem per hour at 3 feet from the package, the transport index is also written as 10. You get me? So they write 10 there. If the dose is 10 millirem per hour at 1 meter or at 3 feet away from the package. Now, what is the significance of the transport index? So for institutions that produce many and transports many radioactive packages, it is a rule that you should only transport a total of 50, that's 50 transport indices per vehicle. So if you have transport index of 10 and you have 10 packages of that, so 10 times 10, you cannot transport all of them at the same time. You need only to transport 5 of them. So you total the transport index or the transport indices of the package. And the rule is it should not be more than 50 or 50 transport indices. You get me?
Yes, sir.
Okay. Now, what is the significance of the number 7 there, Jem?
I did not search about
Okay.
it.
7, guys, is identified for transport of radioactive sources by the International IATA, Airline and Transport Association. Remember, these are universal or recognized by a lot of people. So when you transport a radioactive package by air or by sea, 7 is the category listed for radioactive sources. So there are category 1, 2, 3, 4, 5, 6, let's say for flammables and so on and so forth. So 7 is assigned for radioactive materials. That's the reason why you have 7 always there. Okay?
Okay, sir. Thank you po.
Okay, thank you. So now, do you understand the meaning of the at surface and at 1 meter or at 3 feet away?
Yes, sir. Thank you po.
Thank you. Please continue.
Ayan. So, these are the three radioactivity levels.
Labels. Transport labels.
Transport labels.
But of course, you don't put them in one package. You only put one type. Okay.
So, we have to go to the technetium-99m. This is a radionuclide isotope that is used primarily for imaging and diagnostic purposes. It was isolated in 1983 from the molybdenum 99 decay. So it was explained a while ago by Sir Nats. It was a product of cyclotron bombardment of molybdenum and has produced molybdenum 99, and it has the molybdenum 99 has a half-life of 2.75 days, which decays to technetium 99.
M.
It
Technetium
is
99M.
technetium 99M. It is the most common radioactive isotope tracer used for SPECT, or the single proton emission computerized tomography imaging of the brain, bones, lungs, kidneys, thyroid, heart, gallbladder, liver, spleen, bone marrow, salivary and laryngmal glands, blood pool, and sentinel nodes. The most favorable property of the technetium-99m is it has a short half-life of 6 hours. Um, the 6-hour half-life and rapid exclusion from the body limit toxic effects and give enough time to perform its diagnostic imaging while limiting radiation exposure to the patient. So the mechanism of action of the technetium-99m, the radioactive isotopes of the technetium-99m exert their effects by emitting gamma rays, which are then picked up by a gamma camera for imaging. The radio tracers are not localized to a primary organ and distribute equally to multiple tissues. Yes, sir.
Is that accurate, that statement, that radio tracers are not localized to a primary organ? Where are you coming from that statement? So you're saying the radio tracer, you're not referring to the radiopharmaceutical?
Actually, sir, the radio tracers are the radiopharmaceutical itself. So, it should localize to a primary organ as yun po yung nade-detect niya, sir, di ba?
Yes.
During that.
This statement, is it referring to radiopharmaceutical or to the tracer itself? Because you might be confused on that.
I will have to check my sources for this one.
Yeah, but I think this should be the radiopharmaceutical
And it should
are
be
localized to a primary
Yes, sir.
organ and then probably distribute equally to multiple tissues. Because if the statement in itself, meaning the radio tracers are not localized to a primary organ and distribute equally to multiple tissues, I think is still incorrect. Because if you are referring, for instance, to iodine 131, it is localized to a primary organ, right? Always.
Yes, sir.
Okay, so
Actually, sir, I guess, I'm sorry, I may have typed incorrect because my next note is that once the radiopharmaceuticals are distributed, they should emit photos that can captured for the imaging. So
yes.
if it is not localized, then it will not be captured with
Correct.
the PET scan.
So I think you should.
Sorry, sir, I will have to.
Yeah. The radio tracers or radiopharmaceuticals are localized.
Yes, sir, are localized.
Probably correct this statement. Okay.
Okay po.
Thank
Sorry
you.
po.
Yeah, it's okay. Thank you.
For the administration, the technetium-99 radio tracer may be administered via intravenously or orally, and dosages may be modified depending on the patient and indications of the imaging. It is safe to administer in adults, and with children, it should take extra precautions and proper monitoring.
Jem, can you add in the administration also through inhalation?
Okay, sir, I will add it.
Just to cover those radiopharmaceuticals that in gaseous form.
Thank you,
Thank you.
sir. So, adverse effects. Technetium-99 can cause rash and angioedema, fever, and anaphylaxis due to hypersensitivity reactions. Patients may also experience a transient increase in blood pressure, seizures, arrhythmias, and syncope. And when used in abdominal imaging, abdominal pain, vomiting, and diarrhea may occur. Severe hypersensitivity type reactions may occur shortly after following the administration of technetium-99m.
Just for your information also, I have not heard yet of any adverse reactions to technetium-99m in any of the nuclear medicine departments. Okay, maybe very, very, very rare would you find such adverse reactions to technetium-99m in the local scenario. Okay, so maybe these are also some rare effects, but should also be taken noted of, especially by the different nuclear medicine technologies. So that just in case this happens, of course, I think GEM is going to the ways on how you can control them or counteract them. Please continue.
Okay, sir. So, for the hypersensitivity po, the administering nurse or physician should have corticosteroids and antihistamines at ready in the event complications do arise.
Okay, just to mention, no, Jem, your resource that there is from abroad because in the
Yes,
Philippines
sir.
you don't often see a nurse in the nuclear medicine department. Very, very few nurses are found in the nuclear medicine department. So as I mentioned, most of the personnel in the nuclear medicine department are medtechs. Okay, so that is on one side. That is also, I think, one aspect for which the Philippine Association for Medical Technologies should look into, or the PAMET, because correct me if I'm wrong, it is mentioned that medical technologies should only extract, right? And not inject something to patients, right? Are you allowed to do that in your protocol as a medtech?
Ideally, sir, no.
Yeah, that's what I'm trying to say. But as I mentioned also, in the case of nuclear medicine in the Philippines, since the very start, medtechs are the ones doing the injection to the patients. However, I think that was just the tradition because initially radioimmunoassay was the main application in nuclear medicine. So they extract blood and prepare the serum for detection of the antigen antibody reactions. And maybe that is also the main reason why the doctors in nuclear medicine department prefer to employ medical technology licensed medtechs for that matter. But I think on the side, PAMET should look into that, right? Jem,
Yes, sir.
I've talked already with President Mr. Mel Saceda to look into that also. Anyway, so that means abroad, it's either the nurses or the so-called radiologic technologists that are in the nuclear medicine department. I have nothing against medtechs being in the NUCMED, but it is the radtechs who would have that study of nuclear medicine in their curriculum. And just recently also, because radtechs are not allowed to extract or inject something to patients, they already, if I'm not mistaken, started 5 years ago to include venipuncture in their curriculum to cover that limitation of their field of endeavor. So, because nurses are the only ones that would have injection or administration to patients in their career or description of work. Okay, so much has to be aligned. I think that is the proper term. Aligned for the med techs, aligned for the rad techs. Okay. However, I think they already are starting that because, as probably I've mentioned this before, there is a curriculum and bachelor's degree program. Firstly in Asia, and that is the Bachelor of Science in Nuclear Medicine Technology, started by the De La Salle University in Cavite. Okay, so it's just a segue of the discussion. Okay, so thank you. Please continue, Jen.
Thank you, sir. Um, I think this will be my last slide. For the contraindications, technetium 99 is not permitted to use when the patient is pregnant, as there are not enough adequate studies in pregnant women. Breastfeeding is also a contraindication to its use, as 10% of the agent may be excreted in the breast milk during lactation. That's the end of my
Thank you. So,
report.
for the slide that the last slide that Jem has mentioned, that is the reason why if you go to nuclear medicine departments, there are posters and signs all over the center saying that if you are pregnant or suspect to be pregnant, you have to inform the nuclear medicine staff. Okay, whether you are the patient or just accompanying a patient, you have to inform the nuclear medicine department. Okay, for the people who accompany the patients, the reason is because we do not want occasions of patients blaming, let's say, them being in the nuclear medicine department, thinking that they might be exposed unnecessarily to radiation during the accompaniment of their friends or relatives who would undergo nuclear medicine procedure. But you would probably note that if they are accompanying their relatives or friends for a nuclear medicine diagnostic procedure, the levels of radiation doses that would be received are not that significant. And the evidence of that is the fact that after a nuclear medicine diagnostic procedure has been performed on a patient, the patient can go home, okay, and do his or her usual activities, can mingle with family, with relatives and or friends. Okay, so thank you for that report, Jem. Are there any questions from the rest of the class? I see a question by Peter. Okay. Peter asks, and Jem is also directed on this question. What is the difference between a contrast media and radiotracers? Do both localize to tissues and spread to other tissues? Can you answer that first, Jem?
Hello po. Ayan po. I have read po before that contrast media po are like chemical substances then they're like agents or dye po. And as well as the radio tracers It has a radioactive tag din po and targeting agent. It may answer, Sir Nets, please correct me if I'm wrong, but yes, they both localize the tissues and spread they both localize the tissues and spread to other tissues. But I think the difference lang po with this is the contrast media is used usually in X-ray and MRI.
Okay. So, yes, Jen, your answer is correct. The main difference between the two is that one is not radioactive, meaning the contrast media is not radioactive in itself, and radio tracers are radioactive. Okay. Uh, of course, another difference would be in the fact that contrast media, as the term suggests, uh, are used to create contrast in the images. Okay? And they both localize in certain organs or tissues. But the main advantage, if you could call that, for radio tracers is that it will provide us with information that are physiologic. While for contrast media, they are only there to provide the contrast and would not talk of any functional information because they are used only for, uh, as what Jem has mentioned, diagnostic radiology or commonly called X-rays, or for MRI. Of course, they don't use X-rays, but are there to create that contrast, meaning you can tell the difference between a certain structure of the body to the others. Well, to further illustrate such materials that are not radio tracers to create contrast, one example would be a barium based chemical that are drunk by patients in diagnostic X-ray to visualize, let's say, the esophagus. Okay, or barium enema that is provided to patients also in diagnostic radiology to look into the structure of the intestines, no? The large and the small intestines. Okay. Now, also that is used in magnetic resonance imaging or MRI to create the contrast. Okay. Now, for non-ionizing radiation, aside from MRI, another common contrast medium, if you could say that, would be in ultrasound. I don't know if any of the ladies, sorry, have experienced undergoing an ultrasound procedure, let's say, of investigating the reproductive system of the ladies, no, wherein you are asked, no, to drink a lot of water. Anyone has experienced an ultrasound procedure, especially for investigating the reproductive system or the cervix area?
Me, sir, I have experienced that, but that time po, I got admitted po because I had severe GERD na po. And then the doctor was worried baka it's not GERD, it's about my gallbladder na po. So, he ordered ultrasound po and then before po ako mag-undergo ng ultrasound, pinainom po ako ng isang
Maraming
basong tubig.
Yeah,
Opo.
not necessarily just probably one, but a big volume of water. Now, water serves as a so-called acoustic window for the bladder for the ultrasonologists or the sonologists to visualize, let's say, the cervix. No, so they are used to serve as a contrast medium, and I think also that is experienced by some male patients. They're also asked to drink water to perform certain ultrasound procedures. So that is an example. And of course, we know that that water is not radioactive. So the water that was drunk is used to create some contrast and not considered as a radio tracer. So the main difference would be radio tracers, as the term suggests, would include a material that is radioactive. Okay, so it is radioactive. The contrast medium is not radioactive. Does that answer your question, Peter? Okay, you're welcome. So are there any other questions to Jem or to me as regards to that? To the quality control in radiopharmaceuticals? And Jem has mentioned and touched a lot of other QC tests that are performed on radioactive materials. Okay, so again, to note, after us knowing how to produce a radioactive material from nuclear reactors, cyclotrons, and generators, what we produce are so-called radio active materials. Now, these radioactive materials, if we want them to be used in nuclear medicine and to be used for the investigation of certain functions of organs of interest, we have to combine them with some chemical compounds that would be going or concentrating to certain organs of interest. Now, when we do that, the process of combining a radioactive material and a chemical compound is called, the product is called a radiochemical. Okay? It is a radiochemical. Now, Jem has mentioned to us that for it to be considered as a radiopharmaceutical, it should undergo certain tests so that it is informed that can be administered to patients, meaning they should be sterile, meaning not be able to cause any infection. They should also be test for pyrogenicity, meaning we should check on whether this radiochemical is not able to create and produce fever to the patients. They should also have a certain level of pH that is used. It should be radionuclidically pure, meaning it should not contain any other radionuclide in itself. Okay? I think I should also mention this, that another characteristic of radiopharmaceuticals is that it should also be carrier-free. Carrier-free. What does that mean? Carriers are actually stable isotopes of the radionuclide. Again, carriers are stable isotopes of the radionuclide. So, for instance, if you talk of technetium-99m, it should be carrier-free, meaning it should not contain any technetium isotope that is not radioactive. Because what the patient is buying is technetium-99m, and that's the reason why it is checked for its radionuclidic purity, it is checked for its radiochemical purity, and so on, so that it should not contain any other things other than technetium-99m in significant amounts. Okay, so just to add the term of being carrier-free. Okay, so a lot of these are performed, and the frequencies, as mentioned by Jem, can either be daily, some are done monthly, weekly, annually, semi-annually. It depends on the workload of the nuclear medicine center, or of course for the necessity of the requirements set by the competent authority. Okay. Any other questions? Uh, is Earl around? Earl? Is Earl present? I think she's not in the loop. Josh, can you also put that in the group chat so that she will be prepared for next week for the report? Okay, thank you. So I'll just present and do a summary of what has been mentioned earlier, or is anyone in the list ready to do the report? JM, are you ready? JM is also not in the platform anyway. No, JM is here. JM, are you ready for the report? Not yet, okay. So please be ready also next week in case Earl is not ready, JM. Okay, Jem, can you submit to me a PDF file of your report through email?
Yes, sir. I will
Okay.
submit po later. Thank you po.
Okay, thank you. So let me just do a summary of what has been mentioned earlier. Okay, let me present. Okay, so this is just a summary of what has been mentioned by Jem earlier. Okay, so again, the emphasis on the fact that a radiopharmaceutical is a mixture, if you could use that term, of a radioactive compound, some linker, and some targeting molecule to go to, let's say, something. Now, this figure is also good enough for another application of radiopharmaceuticals specifically for treatment, for treatment. And this is the newer trends now called targeted therapy, or can be mentioned as what we will hear later on in the report on theranostics. Okay. So just to differentiate what quality control is and what quality assurance is, of course, these are two terminologies that are very much different because QC, as Jem has mentioned earlier, would be a set of procedures or a procedure to intend some sort of a level of quality, meeting some requirements of the client or some standards. Okay? Now, quality assurance would refer to a bigger set of requirements that would cover the whole process. So QC is different from QA. QA is bigger than quality control because you can perform quality control procedures for several aspects of a certain endeavor. So you can do QC of your equipment, you can do QC of your procedures, you can do QC of your records keeping, you can even create quality control for just the scheduling of your patients. No? So QC is more specific than quality assurance. Okay, so these are some ways to ensure that ideal thing called quality. So you have a process development, you conduct spot checks either on the process or on the equipment. Okay, you maintain, let's say, a conducive working environment. You want, of course, QC on the training aspects and the proficiency of the service that you are performing. Okay, so that is evidence to my statement that QC is very, very specific. Okay, now this is referring to radiopharmaceuticals as extensively described by GEM. It is good only as the care is taken for each of the preparation. Okay, one thing that I recall from the report of GEM is that for you to attain sterility, of course, the other auxiliary processes that you do, let's say assuring the clean environment, assuring the sterility of the materials like the vials that you would use, and so on and so forth, should also be there. Okay, so it is also a process in which a sample of manufactured goods are tested to ensure that it meets its standard specification. So you know that when you buy something according to their specs, you need to assure yourself that it is what you are getting and what you have paid for. Okay, so in terms of nuclear medicine studies, this should be done to have an effective delivery of the service and assuring yourselves that there are no unnecessary radiation exposure, not only to the patient but also to the technical staff. Okay, so this is just a schematic of what has been mentioned earlier by Jem, talking of chemical purity in terms of the pH values, the osmolality, ionic strength, specific chemical impurities, okay, the biological test for sterility, pyrogenicity, affinity, of course, radiochemicals, radionuclidic purity, and so on and so forth that were mentioned earlier in the report. Okay, so these are just some of the terms that were often used earlier. So radionuclide generators are systems that create the shorter lived daughters. Okay, our very good example would be molybdenum 99, technetium 99M generator that is more oftenly used. Okay, radiopharmaceutical precursor produced for radio labeling processes. The kit, these are kits are the chemical compounds that are used to be complex or mixed with the radioactive material, because in the early times of nuclear medicine, guys, the nuclear medicine department that buys their generators are the ones also complexing or combining the non-radioactive kits or chemical compounds uh, to be mixed with the radioactive material. And then they are the ones who test uh, the produced radiochemicals so that they can be compliant to the listed and mentioned conditions for it to be considered as a radiopharmaceutical. Okay, so some other terms: critical organ is the organ or tissue that would receive the highest dose, and ideally this is what we would like to investigate. So critical organs would include, as mentioned by Jem earlier, the brain, the thyroid glands, the heart, the lungs, kidneys, bones, mammary glands, sentinel nodes. Okay, okay, and the radioactive concentration would be the solution that would refer to the amount of radioactivity per unit volume. Okay, some other terms. Don't worry, guys. I'll try to send you a PDF file of this later on. I'll just write that. Okay. biological half-life and effective half-life. If you would recall, effective half-life is that half-life that would take into consideration both the physical half-life and the biological half-life. And of course, this is the description of our biological half-lives. Okay. Some other things about radiopharmaceuticals, and this is a schematic of where the different radiopharms are used, let's say, and different radiopharmaceuticals to investigate, let's say, the brain. You could use, let's say, carbon 11, nitrogen 13, oxygen 15, which are positron emitters. Again, also fluorine 18 in FDG, selenium, technetium 99M, HM-PAO, ECD, and of course the thyroid. Now for the liver, the kidneys, okay. So you have DTPA, MAG3, and sometimes DMSA, okay. For the bones, you can use technetium sulfur colloid for bone marrow scintigraphy, or for the liver also, okay, seen here. So this is, I think, a helpful guide for you to recall the different. Of course, they also use technetium 99M labeled phosphates for the bones, okay, for the bones. So these are the characteristics of radiopharmaceuticals for their use. Okay, half-life, they should be as short as possible for diagnostic purposes. They are ideally gamma ray emitters so that they can come out of the patient and have some sort of a non-invasive sense, meaning you will not open up the patient to investigate the function of that organ of interest. Of course, OJ or alpha particles for treatment, okay, but not for diagnostic purposes. They localize largely and quickly, and they are stable. And Jem has mentioned that radiolysis should not play a very significant role, especially in the combination of the radioactive material and the chemical compound. Okay. Of course, other factors should be the cost and availability, of course, and mainly the safety, because later on, as what we will hear on the report on radiation protection in nuclear medicine, the radiopharmaceuticals that are used should be creating doses to as low as reasonably or responsibly achievable levels. Okay. So some other lists, again, the emphasis on color and clarity, but as I mentioned, I have asked Jen to look into the reference on the allowable levels of discoloration, especially on the yellowish color for certain radiopharmaceuticals. Okay. Particle size and number, especially for tests that would involve, let's say, investigating the functions of the lungs. Okay, the pH ideal is 7.4. Strength and isotonicity, osmolality, and so on. Okay, of course, the radionuclidic purity that has been emphasized also earlier. Okay, we do not want any other doses seen in the administration to the patients, because for instance, if the half-life is longer than what is needed, then that is not following the concepts of ALARA. Okay. So these are the consequences of having impurities, especially on the imaging part, because they could result in non-uniformity or poor quality images. Okay. Radiochemical purity, Jem has mentioned such machines that can be used to attain data and check on the radiochemical purity. So you have HPLCs, the GCs, and some other things like the TLCs. Okay, so some radiopharmacies of nuclear medicine departments that create their own radiopharmaceuticals may have several of these. For instance, they can have an HPLC, they can have a TLC or a GC all at the same time. Okay. So there are also some labels that were also mentioned earlier. Okay. And this is the label on the outer package. Okay. The three types of label, transport labels, category 1 white, category 2 yellow, and category 3 yellow. Okay. Of course, storage is also an important aspect. Okay. Now, this is a list of the different some radiopharmaceuticals and their mechanisms of localizations. For instance, when you talk of colloids, they normally concentrate onto the liver, for instance, because of phagocytosis. Okay, thallium-201 or iodine-131 for that matter is taken up by that organ through active transport. So if you talk of thallium-201, it concentrates in the heart primarily because of active transport. If you use iodine-131, it concentrates in the thyroid gland primarily also because of active transport. Okay, so there's also compartmental localization like technetium-99m RBCs. Okay, for checking on blood pool studies. Okay, and antigen antibody complexation by radio labeling the antibodies. Okay, radio labeling the antibodies. Okay, again another list of the different radioactive materials and their uses. Okay, I would just like to make mention that some of them are used even for reducing pain. Okay, like samarium 153. Okay, or lutetium 177 for different neuroendocrine tumors and prostate cancers. I think this statement that they are currently in clinical trials is not anymore accurate because now, because of the advent of theranostics, they are used uh, for patients already. No, lutetium 177. Okay. Some other radionuclides, and I see here a list of positron emitters like carbon-11, nitrogen-13, oxygen-15, fluorine-18. Though in the Philippines, we only find fluorine-18 that is mostly used in PET imaging or PET scans. Fluorine-18 that is in glucose form, FDG, is very much widely used, if that is a better description now in the country. Though, as I mentioned, nitrogen-13 can be available in St. Luke's system, but they are not often used for cardiac studies, though, of course, it has been documented that nitrogen-13 has a higher specificity and higher sensitivity for cardiac studies compared to technetium-99m labeled pharmaceuticals like sestamib, technetium-99m hexamib, technetium-99m mibis. Okay? The reason for that is because nitrogen-13 in its application for PET may be higher in cost compared to technetium-99m. Okay? And the availability is not that high because of the half-life and its production. Okay? 10 minutes. You cannot supply that. Let's say St. Luke's cannot supply that nitrogen 13 to its St. Luke's nuclear medicine department, say in the global city, because of the half-life of only 10 minutes. So even though the average time for a motorcycle to go to global city St. Luke's from St. Luke's Quezon City is around 30 minutes, so you're losing how much? Okay, three half-lives already has elapsed. And if you would recall, three half-lives would be reduction of the activity to 50, 25, okay? 12.5% would be the activity remaining. So that would be not uh, viable for transporting nitrogen 13, let's say, from St. Luke's QC to St. Luke's Global City. So that is only used, let's say, on-site in Quezon City. But as I've said, uh, it is not that popular because of the cost. Okay, so of course we don't find iodine 123 because of how it is produced. But of course, thallium 201 is there. Okay, it's also used as mentioned also by Jem earlier. Okay, so I'll provide you with the PDF file of this later. Okay, any other questions, guys? Uh, let's have a 10-minute break and then maybe we can discuss the assignment. We still have time, right? Guys, 10-minute break. Okay,
Yes, sir. Yes, sir.
okay, okay. Are you back, guys? So, uh, maybe we can discuss some of the recent assignments that were asked of you to submit. Uh, let me share my screen first. Okay, so this was the third assignment and it consisted of two questions. Well, one is this one. So I'd just like to remind for those people who have not submitted their assignments, please do so. Okay. So for the first one, you're asked to discuss the different factors that affect efficiency of counting systems. Okay. Factors that affect the efficiency of counting. Of course, this would include geometry, the distance from the source, and so on and so forth. Okay? And of course, the inherent efficiency of the counting system itself, meaning the type of radiation detector you are using. Now, for the second question on asking you what survey instrument are you going to advise for procurement. Okay, so survey instrument. Okay, so for survey instrument, of course, you're asked what you need to focus would be on the two types of survey instruments, which are the uh, area monitors or your contamination meters. So area monitors, of course, and contamination meters are two different types of survey instruments. So you're asked to uh, suggest and advise on what types of survey instrument, meaning if they should be GM detectors and other aspects of uh, what GM detectors would be advantageous for the use. Okay? Or you could also talk about scintillation-based systems. Okay, so you have to discuss a lot of them. But of course, it's not only the price or the trending, for instance, that other nuclear medicine departments have saying it should be on the practicality of you getting that. So it's not probably a factor for you to choose. Let's say it's uh, complexity, like it being digitized or digital, no, or just a common needle moving detector or scale. No, of course, it's really up to your pros and cons. The pros and cons would be also dependent on the budget, of course. The digital systems would be relatively costly than the simpler ones. Now, for the other assignment, the recent one, you're specifically asked on the discussion on the description of the dose calibrator, okay, on the dose calibrator, and emphasizing on the considerations during installation, routine use, and quality assurance program that is dedicated to it. Well, I could just mention, for instance, that one important aspect of those calibrators, also as mentioned earlier by Jem, is that it is an ionization chamber that uses electrodes that are very, very thin. Therefore, those calibrators are very, very sensitive to movements. Okay? So, when you are installing it, you have to decide on which place you will place it and not be moving it again if you want to relocate it to another position or area, because even mere 1 centimeter movement of the dose calibrator would require another full range of the calibration related to it, because of the very sensitive electrodes found, especially for the deep well types. No? For the deep well types. Okay. Now, for the second question, you're also asked to talk about how the PET-CT doses compare. Okay, how the PET-CT doses compare with doses from other examination. And you might have noticed, of course, that PET procedures would provide a dose, CT procedures would provide also a dose. Therefore, if you talk of PET-CT, it will provide higher doses. So you just expound on those. Okay. Uh, any question to that, guys? Any questions? Any questions, guys? Okay, so if there are no questions, I think next would be Earl in to do the reports. So please, JM, try to contact her and see if she is available. I have not heard from her much. Okay, but also uh, JM, be prepared to do the QC of nuclear medicine instruments. Okay, JM. Okay. Uh, Looking at our schedule, so we would have a meeting on November 26th. Okay, right? So I also would like to ask Sol if you also prepare for that. Okay, for that November 26th for your report. In case Earl is still not able to report on that day. So I hope JM and Sol that you prepare for the discussion for November 26th. Okay? Okay. And up to when is our class? Would you recall, guys, in the calendar? So we will still have December 26th and December 3. Okay. And when is the Christmas break? Guys? Would you know? When is the Christmas break?
Sir.
Yeah.
Based on the calendar, December 18 to January 1, a total of 15 days.
So December 18. Okay, so that leaves us with around 3 more meetings, right? 26, 26, 3, and 10, right? So I do hope that we are able to cover the reports. We're still left with how many reports? We have Earl, JM, Sol, Bong, Sora, and Ken. Okay? I hope we cover them. So we hope to cover so that we will be safe. Earl, JM, and Sol for November 26, Bong, Sora, Ken, December 3. Let's target that, okay? So, JM, Sol, and please ask Earl to provide me with the initial PDF file. I'm sorry, PowerPoint file of the reports. Same thing with Bong, Sora, and Ken. Please email me the initial draft of your reports. So we target to finish by December 3 and leave December 10 just as a backup. Okay, but I hope Bong, Sora, Ken will report on December 3 on their topics. Earl, JM, and Sol next meeting. Okay? Yeah, okay. So if we're not very sure on that, let's provide that timetable. Next meeting, hopefully the 3 reports of Earl, JM, and Sol would be covered, and then the next meeting, December 3, the last 3 reporters, Sora, Ken, and Bon. Is that understood? Then I think the finals will be next year, right? We can prepare for that. Okay. So any more questions? Clarifications? So Peter, thank you for recording. You may stop recording now. And then kindly send me an email